So this is going to be a talk about Apache Kafka, and it's going to be a talk about why it was built, what it's for. A lot of this work was done when I was at LinkedIn. I was there for about 7 years, and I worked on data infrastructure of all types, distributed databases, all kinds of things. But this actually started when we were making one of these data lake things, which it turns out is harder than it looks, I guess. And my job was to fill it up with data. And in the process of doing that, I realized a lot of the complexity about how systems that we had at LinkedIn managed data, all the different formats of data, all these kind of annoying metadata questions. So basically, all the pain that was hopefully addressed in the earlier slides. But I realized one other thing, which is Hadoop isn't the only thing in the world. Data lakes are not the only place that data was going to, at least not for us. And this methodology of kind of dumping data out at the end of the day and putting it in your data warehouse, it makes a lot of sense in certain circumstances, but it was actually by no means the only problem we were trying to solve with data. And there was a whole bunch of issues in what we were doing, from coverage and what types of data there were to all the different data formats, which I think we talked about some of the metadata issues. And then the constant change of all of this as you evolve your software. And so one of the kind of journeys we went through at LinkedIn was really trying to figure out what's the scope of this problem, how could it be better solved? And we kind of did a survey of what types of things we had. So the first type of data we had was things in databases. And we had lots of ways of getting these around. So we had real-time caches and derived stores that would mostly get populated by application changes. Maybe we would pull for changes and populate some cache. We had kind of periodic dumps of like CSVs and stuff for Hadoop. So some of these were real-time. Some of them were kind of batch, end of the day. Nothing was very systematic. We also had logging or user events. This was activities that happened in the business. We would kind of log it out, and we would aggregate these logs. And then, it's much more complicated than this. There was data centers, but somewhere in here, rsync would happen, and NFS devices would fill up and overflow, and eventually data would get into Hadoop. And then we had a whole bunch of data about our data centers and operational stuff, monitoring data, like Splunk and application logs, not like what our users were doing, but what errors had occurred. And that stuff never made it to Hadoop at all. It just made it to some monitoring system. And we had a set of messaging systems which were used in kind of an ad hoc way. So we were using ActiveMQ. So this was kind of the state of our world at LinkedIn in roughly 2007. So we had all these things. Each of them solved some problem. Some of them, at least when we adopted it, some of them were real time. Some of them were offline. Some of them were fairly scalable. Some of them were more or less correct. None of them were all of these things. And when you put it all together, it was kind of a big mess. So if you wanted data in Hadoop, you would basically kind of wire up these different databases and dump data out to Hadoop. The same thing was happening for a data warehouse. Messaging systems were kind of a dead end in their own right. Any kind of operational monitoring was totally different. Any kind of non-relational database was very poorly integrated in all of this. And you kind of get this n-squared connection problem where everything is kind of trying to connect to everything else, but of course you never really get there because it's too hard to build. And I was actually responsible for part of this, which was the let's get it into Hadoop part. And I wanted to try and find some kind of infrastructure solution for this. So I didn't really want a consulting team where we had a whole bunch of people whose job was to write integrations to data systems and convert it into the right format. You could build, obviously, a very big team that way, but not a very good team. So instead, infrastructure is something where you put a lot of effort into it, and then hopefully you get a lot of use out of it, like a bridge. And so the question was whether we could solve this big mess problem with any type of infrastructure. And we started to really think about this because it's not as easy as it sounds. But we did come up with some idea. And the first idea we came up with was you could really treat all these different data types I talked about as some type of event. So maybe a log file is pretty obvious. It's like a list of events that happen, like an error occurred or an error occurred. And logging out of activity is the same way. But you can treat databases the same way. So I don't know if everybody knows what change data capture is. It was in the last talk. But change data capture is basically a series of updates to your database. It says the value of this row is now this. The value of this row is now this. And application metrics, logging, basically everything we had was some sort of event. It was like a new record was created. And these records, you can imagine them just having being like JSON and having a timestamp and some fields. And so one way we could kind of think about all these things as being the same is saying, well, basically we just have a bunch of events that are occurring, and all these data pipelines are some type of event stream. So a database that's accepting updates is a stream of, hey, now this record is this, now this record is this, now this record is this. A log file is a stream of error, 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 or hopefully okay, 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 but usually error, error. If you're tracking clicks, it's click, 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 click. And so you can think of all these different types of data that we had from all these different systems, and if you just kind of squint a little bit, you can say, okay, what we really have is not 40 different problems. We really have one problem, which is just streams of events. And furthermore, if we had some kind of place where we could put all these streams of events, we could make that picture, that big mess picture, a lot simpler because we could plug everything into these kind of central streams. And so you might capture changes coming out of a database. Maybe that goes to some kind of search index, and maybe it also goes to some kind of real-time monitoring thing, and maybe it goes to the data lake thing, which was the whole subject of the last talk, the data warehouse and Hadoop area. And wouldn't that be great? And so this was our thinking. And the question was really just, okay, great. How could we make some type of streaming platform like this? And there's some advantage to this type of central hub architecture, which I'll just walk through an example of. And the advantage is you start out with some piece of data. So LinkedIn has jobs, and you can view them. So one event at LinkedIn would be, oh, somebody viewed a job. And maybe the first use you have for that data is you want to put it in Hadoop, your data lake. And so you would start out by basically publishing this stream of job views, and it would just go to Hadoop. So it's pretty straightforward. But one of the things we found with data was it never ends up being simple over time. And so as things evolve, it's very often the case that you would have other ways that jobs could be viewed. Maybe instead of a web app, they can be viewed on a mobile phone or through APIs on third-party sites. And the uses for that data, instead of just being something that you kind of run a report on every day, that could end up being something that is checked for security so people aren't scraping your site. Maybe people who post jobs, you give them some kind of analytics page so they know if they got their money worth or not. Maybe you do job recommendations, and maybe you monitor all of this because you monitor everything. And so that was really our motivation, was this idea that this central hub, each area application system could publish its kind of stream of events, and everything else could plug in. And so we spent some time trying to build this, and we started out with off-the-shelf messaging systems. So we started out with ActiveMQ, because we already ran it, and we tried out RabbitMQ. This was a while back, so I'm sure all of these things have gotten better since then. But we found that these things were not really a great fit for the type of use case we were trying for. So the first problem was we were really trying to log kind of everything that was happening. And so the size of the data was actually quite large. And that meant we were going to be doing it over a pool of machines. Secondly, we were going to be doing this for important data as well, stuff coming out of databases, so kind of core transaction streams. And we needed to have things like ordering and delivery guarantees that were relatively strong. And we needed to be able to do this in a fairly scalable way because we had a lot of data. So those were the problems we had. Our solution was eventually, after kind of struggling this for a while, was really to try and build a system from scratch. So we thought we would take what we saw in a system, like a distributed database or Hadoop, which really kind of stores data that's happened in the past, and we would take something like messaging systems, which are all about delivering messages that are sent in the future, and subscribing to that and try and combine it and make some kind of platform for streaming data that would kind of meet the needs we thought we had. And what we came up with is not that different from a messaging system or a Hadoop cluster or a database. I mean, there's a cluster of Kafka servers. This is what Kafka is. And you have things that produce by writing and sending data over the network into this Kafka cluster. And you have consumers which subscribe to these feeds and react to them in some way. And that's what Kafka does. So in that respect, I guess it's like every other kind of distributed thing. But internally, the abstraction it provides to you is actually really different. So the abstraction it provides is this type of log. And I mean the word log. The word log is like heavily overloaded. So I don't mean like an Apache log necessarily, like a text file. I mean like a commit log in a database, so like a sequence of records that are ordered by time. This is my attempt at depicting, in my really bad handwriting, a log. And each of these rectangles is like a record that's appended. So this would be one of those events. And the format of the event doesn't matter. You can just pretend it's like JSON, or it doesn't matter. It's some kind of data. It's bytes. And new records will always get added to the end of this log. And people who want to read this data, they kind of read from left to right. So a log is just this kind of ordered sequence of events. And the nice thing about this is you can have lots of people who kind of subscribe or read from this log. And they can each be at some point. And each of these records gets its own number. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And the position that any of these readers is at is just kind of its number. This guy is at 7. This guy is at 9. And new writes come in at the end. So that's what a log is. And it turns out that this is a pretty good way to implement that type of publish, subscribe messaging pattern I was talking about. So if you change the word writer to producer, and you change the word reader to consumer, then that's how it works. The people who want to subscribe to these message streams, they're going to be kind of reading from left to right. And as messages come in, it will just go to them. And so you can have this single log of what happened and share it across multiple consumers. And that is pretty much Kafka's data model. So in Kafka terminology, you have a Kafka topic, which is some kind of logical feed or category of data. So at a company like LinkedIn, you would have something like page views or searches or profile updates. And that topic would be split over some partitioned log. And it's partitioned really to give you kind of parallelism and spread it across machines. So maybe in this example, I have 3 partitions, but maybe you would really have more like 100. And this is pretty much what there is to know about Kafka. It also has a mechanism for managing groups of processes that subscribe to the feeds. So obviously, if you're going to have these kind of big scalable feeds, you need to have some way to scale out the things that read them as well. So it has that. I'm not going to go into the mechanics because it's more detailed, but there is that mechanism. And the most important from our point of view was to really try and implement this as a modern distributed system. So as something which would kind of have the capabilities that would make it possible to really run this at company scale for the use cases we had in mind. So the first criteria was really that it would have scalability similar to a file system. So unlike the messaging systems we tried, it needed to not get slower as you added data to it, which is really important, right? If you're logging out stuff as fast as you can. It needed to be able to handle writes at hundreds of megabytes per second, or whatever rate you would consider for logging. And it needed to be able to handle many terabytes of data on commodity hardware per server. And all of these were important for these really high volume use cases. So if you didn't have these properties, then all this kind of like event logging stuff would be off the table, and you'd have to have some specialized system for that, and then maybe something for the important stuff. But the important data actually needed strong guarantees. So it wasn't enough to make it cheap, it also had to be correct. Meaning you have to order updates. So if I'm propagating changes to user profiles, I have to propagate them in order. If you update your profile and you update it again, the search index really needs to get first the first change and second the second change. If it gets them out of order, it's going to have the wrong result, and the search won't work correctly, right? So you need to be able to order updates, and you need to be able to do persistence or durability or delivery guarantees well, right? So if we're counting on this to not miss updates, it has to work. And second, we wanted something which was distributed by design. So something that was built to be operated as a cluster, where you would assume the data was replicated, where you could add machines to it and expand it without bringing it down. Kind of all the modern distributed systems stuff that you would kind of take for granted in any new piece of infrastructure, but wasn't necessarily there for anything in this kind of messaging space. So that was what we came up with, and that was really this stream data platform. That was this kind of central place where we could keep all the streams of data that could feed all these different areas. And I'm going to dive into one of the areas, because when we started this project, we really had two goals. One was to make it kind of a universal data pipeline that would get data from place to place. And we were pretty sure we needed that, and we were pretty sure we knew exactly what the requirements were. But the second goal was actually this whole area of stream processing. So we had a kind of hypothesis, which was, hey, we currently, when we started the project, we thought, hey, we currently don't really do any real-time processing of data. We have services, which respond to requests, and then we have like batch jobs at the end of the day. And so in between that like instantaneous request and the 24-hour delay, there's like a big gap in which there's no real infrastructure. And we thought like, hey, it would make more sense if we did a lot of these things in a streaming fashion. It would actually be more useful, in many ways easier to build against and so on. But the problem was, it's a bit of a chicken and egg problem. Like, at that time, we had no streams of data, so naturally we didn't like process streams. If we had them, would we actually process them? And it turned out that, indeed, that turned into a pretty big area. So as we started to capture streams of data to get them around from place to place, this whole ecosystem of stream processing really took off. And it was good that we had kind of thought through the use cases around it and the abstractions that stream processing would need, because otherwise, I think that wouldn't have been possible. So I'll go just super briefly through what stream processing is, and a little bit about how Kafka supports it. First of all, I'll just give kind of a really brief introduction. So if you see a query here, there's like a SQL query. We would normally think about this as running against some static fixed data set. So you would have a file in Hadoop, or you would have a table in a database, and this query kind of scans over all the data, and it computes some results, and when it gets to the end, it gives you the answer, right? And then it's done. And that's great, but if you actually think about data in organizations, in order for this query to run, the table has to sort of be static, right? In order to get to the end of the table, there has to be like an end. It has to stop being updated. And so, of course, the magic of databases is they'll kind of lock and freeze and pretend that nothing changes so you can get to the end. Or hopefully, hopefully. And the idea of stream processing is you could actually kind of turn that on its head, and you could take this query, and you could instead kind of stream the data through the query and produce results. So this is a query on add clicks, and you could essentially run this query forever, and you could stream clicks through it, and it could continually produce its aggregation. Both of these views are super valuable, but I do think that this view is actually pretty important and a little bit neglected. And it's actually a relatively powerful concept. So most things that we compute in other fashions could be computed in this streaming fashion. And for a lot of modern use cases, it actually makes a lot of sense. But the first thing to understand is, of course, you can only do this if you have kind of streams of data available. So if all you have is batch data collection, if you just like dump out CSV files at the end of the day and put it in Hadoop, there's no way to like stream process it. Like you will just have a batch file at the end of the day, and then you can't stream it. We actually ran into this when I first got to LinkedIn. This company came to sell us this like cool stream processing language, and at that time we really had no streams, and we tried to come up with something to do with it. All we could come up with was, at the end of the day, when we collect all the files, we will stream them into this framework. And then we decided that really didn't make any sense, and we should just load them into the database. On the other hand, if you have the streams, you can totally do that. And it turns out that this log abstraction I gave is actually really important for being able to do stream processing. So in some sense, by introducing this notion of time to these records, you can really kind of unify this idea of batch processing and stream processing. So batch processing is kind of like we scan the file to the end, we process and we give you your answers. And stream processing is we scan and we process, and then we just kind of keep going. So it's like that query I showed would just kind of produce results and then just keep producing results, like it would never stop. As records were added to the end of this log. And it's practical, it's important for practical reasons too. If you want to develop some kind of stream processing thing, you need some data to run your program on. And if you're just like waiting for future data to come in, that won't work. So you actually need this kind of historical record of what happened combined with this subscription to the future. So this idea of this almost infinite log of changes going forward is really important for implementing stream processing. And one of the reasons I think this is so interesting is not so much just like the infrastructure perspective or little parts of how you could use this for whatever. It's actually, if you kind of step back and you look at how businesses work, I think businesses are mostly inherently real-time. Like your things are happening in real life in real time. They're mostly not batch processes. So an example I'll give is like retail, because everybody understands, or at least they think they understand how retail works. So you have sales and you have shipments, which are fundamentally events that are happening. You have some process which is maintaining inventory and keeping track of what you currently have on hand. You have some process which is maybe adjusting prices and deciding to raise or lower prices. You have some reordering decisions that are coming out. You have analytics and fraud. And you can actually think of this as a continuous stream in computation. You might implement that continuous computation as something which just like runs at the end of the day and produces output and then runs the next day. But that's kind of a weird artifact of like how technology developed. It's not inherent. You would actually think about this as a continuous process if you kind of thought it through from scratch. And I think as businesses have become more digital, we're going to see a lot more stuff in this stream processing space. Just because A, it makes more sense, and B, kind of users, customers, a lot of use cases kind of demand it. So how does this relate to Kafka? Well, it's relatively straightforward. If you think of those Kafka topics or logs, you can think of subscribing to this, and you have your code here, which produces some kind of transformation of data and publishes a new topic or stream, right? So this is kind of what I mean by stream processing. And you could chain these, and you could have lots of transformations. And this idea is probably pretty common to people who are familiar with Unix. So in Unix, you can kind of string together these little programs with a pipe symbol, and it will kind of stream the output of one program to the input of the other, and so on. This is actually very similar, except that if you think of Kafka as a type of pipe, first of all, it's a multi-subscriber pipe, which is more like a named pipe if you're a super Unix nerd. It's also distributed and over the network and all that kind of stuff. But that makes sense if you kind of translate where Unix came from. This is a big mainframe you would all kind of log into and do your work. And in a modern world, you're not doing all your work on a single computer, so you want this to be kind of a distributed version of Unix pipes. And there's a whole ecosystem kind of emerging around this. So this is a Kafka logo. So if you think of Kafka as being kind of a stream and holding this stream of data, there's this whole emerging set of stream processing things which attempt to provide some kind of application framework for doing processing on top of streams and make it as easy and convenient as all the batch processing frameworks. It's probably not there yet. There's a lot to do there, but it's kind of getting there. So this is my attempt at a formula. So you have stream plus processing equals stream processing. This is really technical. OK, and here's the kind of resulting architecture we ended up with. So this is the kind of like after picture. I had the big mess picture. So in this world, this is at LinkedIn, we had Kafka. It was this kind of central pipeline. It connected the Hadoop data warehouse kind of offline batch data lake world with the kind of like request response systems. And around it was this whole kind of real-time streaming area. So there was stream processing apps that would do all kinds of things from security and whatever. And there was a whole set of analytical things. So log search, security and fraud detection stuff was very much this way. A whole set of real-time analytics and monitoring tools were all kind of tapping into these same streams that would end up down here. The real-time stream processing stuff could take these feeds, process, produce some kind of streaming output, which would go back to these request response systems and produce output for people. And we actually scaled this up quite significantly, so it was the primary backbone for data. LinkedIn handled pretty much all the different types of data at LinkedIn. There was over 1 trillion messages that went through Kafka per day, and much more than that read out. And actually, the harder problem is actually it was used by thousands of engineers in a relatively self-service way. This is across data centers with thousands of processes in each data center and all the kind of glorious big data stuff. And it's open source, so it's used at a whole variety of companies in totally different industries. Really fascinating use cases for all of them. And about a year ago, a little over a year now, the team that built Kafka actually left LinkedIn, and we founded this company, Confluent, and we're really focused on building out this whole streaming platform vision and making that something companies can adopt. So we're doing pretty much the majority of the development on Kafka. We're building out kind of all the monitoring and management tools around that, connectors for stuff, just kind of the whole thing, I guess, we had built in-house and that other people we had seen had built in-house as they kind of built out this area and put it into practice. And if you're interested, you can check out our website. We have a super active blog and a bunch of kind of off-the-shelf open source tools. So Confluent platform, which is the thing we produce, is basically a whole bundle of open source things for getting going in this area. And if you like this stuff, there's going to be a Kafka Summit, which is coming up in April, and it'll be in San Francisco, and you can learn all about this whole area of stream processing and all about like use cases from different companies that are coming to present. So definitely check that out. The Confluent platform stuff, weirdly in this presentation, all URLs have been like detected and removed. So it's not /download. If you put that into your web browser, it probably won't work. There was something here, which was like confluent.io. OK, so that's useful information. If you're interested in the streaming area, we're also hiring. And that's all I got. I'll be around for questions after. Thank you so much.